When discussing the concept of arc length, you have to kind of keep in mind that a length is a lineal distance that's being measured. So if we look on a coordinate plane, and let's say we just have this relatively generic function, we'll call it f of x. If we want to measure the arc length, what we're doing is we're measuring the distance from start to end along that contour or along that shape. So it would be like having a flexible tape measure and measuring along that curved surface. So if we think about that, then from a Cartesian standpoint, from a standpoint of this being the y-axis and this being the x-axis, when we look at measuring the distance between 2 points on a function, we can arbitrarily pick maybe this point and this point. Then if these 2 points are close enough together, or if the contour is such that between these points, we can almost estimate the contour between the 2 points as a line. And that line's oblique in many instances. And so if we look at then this from a Cartesian standpoint, we really can look at the length of this line as being the length of a hypotenuse of a right triangle. That is connecting the ends of that segment. So of course in this distance we're looking at a distance, and we're just going to call it, actually even before I get to call it a differential, let's just call it delta x. And we're looking at this distance here of that right triangle, which we just could call delta y. And so we could set up a Pythagorean's theorem sort of relationship that says this length here, which I'm going to call s, because that's going to be our variable for arc length. That being the hypotenuse, then we can say s squared equals delta x squared plus delta y squared. So we can just set up a Pythagorean theorem sort of representation of that diagram. And so if we write an expression then for s, then it's a matter of just taking the square root of this expression, which would be delta x squared plus delta y squared square root. And then, so that's the expression for that arc length, or that segment length between those two endpoints. And then from here on out, to get an expression for the actual arc length across the entire distance, it really just boils down to rearranging things mathematically. So in this situation, what I'm going to do is I'm going to divide this entire expression by delta x. And of course, if I divide it by delta x, that would change the value of the expression, and we don't want to do that. So I'm going to also multiply by the same value, delta x. So really, if I'm dividing and multiplying by that same value, I'm really only multiplying by 1, and I'm not changing the expression. Now I'm going to take this delta x and actually move it inside the radical. So if it's a delta x outside, then inside the radical it's going to be a delta x squared. So that means that this expression now becomes the square root of delta x squared plus delta y squared over delta x squared. And that's just to get the bottom, the denominator inside the radical times delta x. Okay, and so simplifying this, as we can see, this ratio is nothing more than 1 plus this ratio. So if we look at that expression is really 1 plus delta y squared over delta x squared. and you probably can see where I'm going with this at this point, times delta x. And so that being the case, then if we take the limit of this as delta x approaches 0, we can replace the deltas with a differential. And so we're looking at an expression now that looks like the square root of 1 plus dy over dx quantity squared, right, because both the top and the bottom are squared. So quantity squared times dx. And so here comes, and this is our incremental delta s. So I really should have had deltas in front of this whole thing, because this is an incremental arc length, as what was drawn on the diagram here. And so as we then integrate this from a to b, we can come up with an expression for the entire arc length, which is this expression right here. So really this is nothing more than Pythagorean's theorem. And we can always change the variable of integration to dy as well. Using the expression to find arc length that we developed in the previous section, we're going to develop this arc length and we're going to integrate it from 0 to 9. So 0 to 9, and 9 is going to be way, way, way off the coordinate plane here. So it's going to be so far off here that I can't even really draw it accurately. And so a good organizational strategy is, we know we need to find the derivative of this. So a good organizational strategy is just to get the derivative of this already set up. So if we take a derivative of this, it's 3/2 times 2, 3/2 times 2x to the, then we have to subtract 1 here. So we get x to the 1/2. So simplifying that, it looks like 3x to the 1/2. And so now we can go ahead and put that into the expression for the arc length. And so the expression from the arc length is, we're going to integrate from 0 to 9. Those are the limits of integration. And it's going to be the square root of 1 plus the derivative squared. So we got to remember to square this. So 3x to the 1/2 squared dx. So when we're looking at this, integrating this, the best thing to do is really to simplify it a little bit. So I'm going to call that 1 minus, I'm going to go ahead and square this. This is 9x. So we've got 1 plus 9x dx. 1 plus 9x, the square root of 1 plus 9x. Dx. And really, we could integrate that using a u sub. That is definitely possible. By letting u equal 1 plus 9x. So that is definitely possible. Although I think for the purposes here, I'm just going to go ahead and use fint to integrate this. So if I get my graphing calculator up here, and go ahead and go into Math 9 to get the fint up there. And this is easy enough to just put right into the fint. So I'm just going to go ahead and do the square root of 1 plus 9x. So there's the function, and the variable of integration is x, and we're going to go from 0 to 9, and the value of that is 54.929. So again, rounding to 3 decimal places, we have 54.929. These very rarely end up being a ratio. Usually they're irrational because of the square root sign, because of the radical. And this is arc length, so it's a lineal distance, so it's just units. We're just dealing with a lineal distance. To find the arc length in this example, we want to go from -2 to 1. So if we look at that on this graph, from an x equals -2, so we're looking at that region here, so this region that is below the horizontal axis. Let me try to draw that a little bit better. So we're talking about that region there that we want to find the arc length of. And again, let's go ahead and find the derivative of the function. The function is right here, just a polynomial function. Go ahead and use your power rule. So the derivative is 2x plus 1. And so to find our arc length here, we're going to integrate from -2 to 1. And that is the square root of 1 plus 2x plus 1 quantity squared dx. And again, I would use the fint capability of the graphing calculator. I think what I'm going to do though is simplify the radical just a little bit so it doesn't look so clunky in the calculator. So we got 1 plus, and if we FOIL this out, looks like we got 4x squared plus 4x plus 1 dx. And simplify, or combining like terms here to simplify this expression, looks like we have 4x squared plus 4x plus 2 dx. So I'm going to go ahead and put that into the graphing calculator. So math 9 to get fint, and I'm going to go ahead and type in 4x squared plus 4x plus 2. Close that off. Variable of integration is x. We're integrating from -2 to 1. And I've got a syntax error somewhere there. Let's go and try to find that. Oh, I've got an extra parenthesis there. I don't need that parenthesis, so we'll go ahead and take that out. There we go. Okay, so the answer there is 12, which is not correct. Interesting. Oh, I forgot the radical. That's what it is. All right, so I think I'll just leave all this the way it is and go ahead and sneak in a radical. So excuse the mistakes, but that just kind of draws to light on how you sneak this in here. I'm going to go ahead and insert a radical. And now that I've inserted that radical, I'm going to have to go over to the right here and insert a right bracket to close that radical. And hit enter, and that is the right answer. So the right answer here is 5.653. Again, always rounding to 3 decimal places. That's the College Board standard. And we'll put some units on that. For this application of arc length, what we're going to do is we're going to calculate the arc length of this curved section of roofing here. And once we get that arc length calculated, we can then use that as, we can use that number and multiply it by the length of the roof and get the total surface area of that roof. And so this would be a real practical application for, if you wanted to re-roof the top of this barn here. So this contour here, which is actually a pretty common contour when it comes to these type of outhouses, is what we call an inverted catenary. And its function is basically exponential, and based on Euler's number. And so nothing changes about the process here. We still do have to find the derivative of this. So the derivative of that is just using the power rule. That's all it really is. So what I'm going to do is I'm going to rewrite this so we can use the power rule a little easier. So I'm going to distribute the 10. So it's going to be 10e to the x over 20 minus 10e to the minus x over 20. And then we can go ahead and take the derivative of that. So let me just correct myself here. This is the function, it's not the derivative yet. So that's just the function. Okay, so taking the derivative of this is derivative of 31, that's constant, so that's 0. Taking the derivative of this, so using the power rule, we're going to go ahead and this is going to be minus 10 times 1 over 20 e to the x over 20. And this is minus 10 times minus 1 over 20 e to the minus x over 20. And so what we have is then, simplifying, we have minus 1/2, 10 over 20, e to the x over 20. And we've got double negatives here, so it's plus 1/2 e to the minus x over 20. So there is the derivative. And then, we have to do a couple of things here. We have to now put that into the expression for surface area. And so this is where, again, I think it's really powerful to use, and we could of course do all this integration by hand, but this is where I think the TI-84 becomes a really powerful tool. So this is the derivative, and so when we put this into the arc length expression, we're going to integrate from minus 20 to positive 20. And it's going to be the square root of 1 plus this squared. And so I'm just going to go ahead and rewrite this. And so we're going to have to square that. And then yeah, so here's the expression for the arc length from minus 20 to 20. And we could go ahead and FOIL this and evaluate this by hand, but I think this is where the power of the TI-84 is really well used, and that is I'm going to go ahead and in y1 put the derivative here, so it's minus 0.5 e raised to the power of x over 20 plus 0.5 e raised to the power of opposite x over 20. So there's the derivative. Let's just review this. Minus 0.5 e raised to the power x over 20 plus 0.5 e to the power opposite x over 20. So there's the derivative. And now I can go ahead and use the fint function, and we're going to go ahead then and integrate this radical. So the square root of 1 plus, and then using the virus key, go into function and grab function y1 and square it. So there's the derivative squared. Variable of integration is x, and we're going from minus 20 to 20. And so that arc length is 47.008 feet, the units here in this problem. We have units of feet. So this arc length is 47.008 feet. And so the surface area then, and we're getting this surface area by basically saying we can flatten this roof into a rectangle. So the surface area is length times width. And so the length of this roof is 100 feet, I believe. Yep. So the length is 100 feet. And the width of the roof would be this arc here, which is 47. So this would be the 100 feet. This would be the arc length. So that's the 47.008 feet. And so the surface area of this roof then is going to be 4,700.8 square feet.